Hello everyone. So today we have a linear algebra problem that we're tackling here. So we're trying to find a basis B of R3 for which the matrix representation of a linear transformation T with respect to this basis B is a diagonal matrix. Okay, for T going from R3 to R3, defined as T of x, y, z, x minus 3y, comma, minus y, comma, y minus 5z. Okay, so typically I don't really like to spend time on theory when I'm doing these videos. Most of these videos are really to show you how to tackle on a particular computation. But for this one, I have to go into the details a bit of why I'm doing the calculations in a certain way. One, for that reason. The other reason is it's a very common question, so I want to just address that. So to answer this question, if I was looking for a basis for which this matrix for this linear transformation would be diagonal, I would say I'd go ahead and try to pick a basis that consists of the eigenvalues of T if possible. Okay, so yeah, we need to have, in this case, because we're going to R3, I have to have constraint our domain. I have to have three eigen vectors that are linearly independent, and I want to go ahead and work with the eigenvalues. And what I'm trying to write here is I'm just saying, why that would work here, because when you would compute T sub B with respect to V1 Vn, which are what I'm calling the eigenvectors, then you would take each of your V1s, V2 Vn's and put them in your transformation. And because V1, V2 Vn are eigenvectors, the image of V1, V2 Vn is going to equal lambda 1 V1, lambda 2 V2, lambda n Vn. Because again, they're eigenvectors. That's what it means to be an eigenvector. And our results are going to be, as you see, and I'm going to write them out as a linear combination of each of the vectors in B. So lambda 1 V1 equals lambda 1 V1 plus 0 V2 plus 0 Vn. Lambda 2 V2 equals 0 V1 plus lambda V2 plus 0 Vn, and etc. Same thing for lambda and Vn. Now, why am I stressing this? You might say, okay, that makes complete sense, but it seems so trivial. The reason I'm doing this is so we can see what each of the coefficients are in front of your vectors. Because when you're computing TB here, you are looking for the coefficients of each of these vectors that form the linear combination. And each of those coordinate vectors, we call them TB1b, TB2b, and TBNB. Those columns make up the matrix that you're looking for, okay? And what I'm trying to get at is, if you take each of your coordinate vectors here and put them together, you get this matrix for TB, and that is in fact diagonal. So if you picked the basis consisting of the eigenvectors, that will work out. Now, does that always work out? Not necessarily, because not every eigenvector has n linearly independent eigenvectors, so it's not necessarily the case that's going to happen here. Now, how do we actually go about doing this computation, finding this basis? Okay, so all I've done here is to show you that if the basis was eigenvectors, you get a diagonal matrix. Haven't found any of the basis vectors yet, though. Now, the way I would do that is I'm going to spell out some steps here. And I think for me, this is what I found to be the easiest, and students as well, from my experience. So first thing, I'm going to find the matrix for the transformation T with respect to S. S is just going to stand for the standard basis of Rn, in this case R3. If you were working with polynomials, then you'd work with the standard basis for polynomials instead. So, and then the reason for this is because all eigenvalues, eigenvectors of a linear transformation are the same regardless of the basis B. That's why I'm doing this. And S itself, again, the basis is the standard basis, is really nice to work with computationally. And how do I figure out this TS? Well, all you do is you put each of your basis vectors in S. So 1, 0, 0, 0, 1, 0, and 0, 0, 1 into your transformation, okay, because that is the standard basis for R3, is those three vectors. Plug them into T, and you would get 1, 0, 0, negative 3, negative 1, 1, and 0, 0, negative 5. And that right there, if you switch those to columns, those make TS, okay? So I won't get into that in particular, but that's how that would work, and I just ask you to review that. So I get this matrix here so I can get the eigenvalues. That's what I'm really using TS here for. And I'm going to grab the eigenvalues, and hopefully you already know how to do that. If not, please watch a video on that I'll link up. So we're going to get, we're going to form delta I minus TS. In your book, usually it's like A here. And I did that, and then we're going to take the determinant of that and set it equal to 0. And I came up with these eigenvalues, lambda equals 1, lambda equals minus 1, lambda equals minus 5. And I'm going to now get the eigenvectors. That's what I really want. And I will get 3 eigenvectors here, okay? That's what I was looking for. So if you let lambda equals 1, so yeah, you're going to go back to the matrix that you formed over here, the lambda I minus TS one, which is basically when you take the matrix with the lambdas and you subtract it by the matrix that was given to you here, or you formed. And you're going to just replace lambda with 1, negative 1, and minus 5, one at a time. And if you replace lambda with 1, this is what you start off with. And you row reduce, and this is your eigenvector. Do the same for negative 1. You row reduce to here. A couple more steps on that one. And 6, 4, 1 would be your eigenvector for lambda equals minus 1. And for lambda equals minus 5, we do the same thing, and you get 0, 0, 1 for your eigenvector for lambda equals minus 5. And just for the record, 1, 0, 0 was the eigenvector for lambda equals 1. And all you're going to do here is just write those 3 vectors, and that's it. And that would be your basis. So if you can find a set of eigenvectors, n eigenvectors that are all linearly independent, from a matrix representation of a transformation from the standard basis here, then that basis will give you a diagonal representation basically for that for your transformation. Okay, that's how that works. And at the end of the day, we're doing this because it's one of the easier forms of a representation of a transformations with a matrix that you can work with. I'm sorry, is some matrix that has diagonal entries. Okay, thank you for your time, and I hope this helps.